All right, so we are down to the last two lectures. Tomorrow is our last lecture for the semester. Okay, there'll be no lecture on Thursday. If you want to use that time to write your test number 6, feel free to let me know, and you can be a free bird after that. Or if you have other commitments, you can focus on that. Or if you don't want to wake up early on Thursday, that's up to you. So either way. All right, so there's only just one more topic to cover here. Okay, so we are going at the right pace. Before I do that, do you have any questions about what we have been doing so far? Or any questions about? So test number 6 will cover everything from 5.5 onwards. Okay. So I'll do maybe like a quick fake review tomorrow, just to remind you of what chapter 5 topics were. But yesterday we were doing some eigenvalue problems. Okay. But in particular, I mentioned some theoretical things about eigenvalues and eigenvectors of an n by n matrix. Mostly that the sum of the eigenvalues is always equal to the trace of the matrix, which is the sum of the numbers along the main diagonal. Okay. And the product of the eigenvalues is always equal to the determinant, which determinant of A. Okay, so not, which means that if 0 is an eigenvalue, then obviously the determinant would be 0. Okay, that would make a lot of statements in the invertible matrix theorem to flip over. Okay, so if 0 is an eigenvalue, which is possible. Okay, 0 cannot be an eigenvector, but it could be an eigenvalue. Then the determinant would be equal to 0, and the matrix A is not invertible. And you know all the statements that follows after that. So that was one of the things. We also talked about the multiplicities of the algebraic multiplicity is the number of times an eigenvalue is repeated. Of an eigenvalue, number of times lambda is repeated, and the default value is 1. So if there is no repeated eigenvalue, the algebraic multiplicity is 1 always. And the geometric multiplicity that is related to the number of eigenvectors, and that's why the word geometric is applied there. Okay. Mg is the number of eigenvectors for that particular eigenvalue, which I think based on the examples we have done, you must be able to relate to the number of free variables you get. Okay. So this is the same as the number of free variables in A minus lambda I. And everything depends on the characteristic polynomial you're solving for the matrix. Okay, so suppose you have an 8 by 8 matrix that somehow it simplifies into the following characteristic polynomial. So lambda minus 2 to the power of 4 times lambda plus 1 to the power of 3 times lambda minus 3. So if you want to ask me, how did you know that? I just made a polynomial, okay, just to illustrate this multiplicity thing. So somehow if an 8 by 8 matrix, make sure that the multiplicities add up to 8. So it's 4 plus 3 plus 1. Okay. Then we have lambda equal to 2 being a repeated root with multiplicity of 4. So that is MA equal to 4. This is lambda equal to -1 with multiplicity equal to 3. So 3 is the number of times it's repeated there. And this one is not repeated, so lambda equal to 3 with multiplicity equal to 1. And the only case where we can even predict about the geometric multiplicity is this case here. In this case, the mg value is 1. Because if there is no repeated eigenvalue, then there is nothing funny going on. Okay. In these two cases, there is no way of saying beforehand what the geometric multiplicity would be. It could be 1, 2, could be 3 in the case of the multiplicity of 4. Okay. But it won't be more than MA. It's always going to be less than or equal to MA. This used to be one of those favorite, when usually during the regular semesters, we have multiple choice questions on the final exams. It's one of those favorite questions there, just to check if students can answer simple questions based on the multiplicities. You could also ask, what is the determinant of this matrix? You just need to multiply all these eigenvalues together. Okay, so there will be 4 2s, 3 -1s, and 1 3. So the determinant of that matrix based on this data here would be something like -48 or something. The eigenvalues are 2 2 2 2, -1 -1 -1, and 3. Okay. So the product of these will be the determinant. That's going to be 16 times 3 is 48 and negative. So those are some of those small questions you could, without any huge calculations, you could just make out of these characteristic polynomial concept. Okay. All right, so that's where we stopped. Do you have any questions about these ideas here? All right, there won't be any multiple choice for your test, but these things are useful, okay, just to keep in mind. All right, let's now start. Hope everybody's here online. Yep. All right, so let's start chapter 7. All this linear algebra we were doing, it's not just for some kind of meaningless fun, okay, because we wanted to somehow tie it together with differential equations, which is what we were doing at the beginning of the semester. So chapter 7, systems of linear first order. D just, I know it's been a while, but D just stands for differential equations. So we started linear algebra by writing systems of just linear equations. These are systems of linear differential equations, and just to keep it simple, just first order. Okay. So suppose you have, say, x1, x2, x3, dot xn being n functions, and let all of these depend on some independent variable, say t, as a function of time. Okay. So depending on t. You can think about this as maybe n species of population or n components in a chemical reaction, all of which are changing with time. So we can write some very simple differential equations based on these. Clear up that later. So dx1 dt equal to a11 x1 plus a12 x2. Okay. So it tells you that your rate of change of x1 with respect to t, it depends on x1, but it also depends on x2. Okay, so it's some kind of a interspecies reaction going on here. Plus a13 x3. Now it's getting worse. So x1 depends on x3 and everything else. Okay. Plus dot 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 plus a1 n xn plus maybe some independent functions f1 of t. And similarly, you can write equations for x2, a21 x1 plus a22 x2 dot 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 dot, dot plus a2n n, okay, plus f2 of t. Again, those coefficients are just written so that I could make use of that later in the matrix. Okay, keep writing it down. Dxn dt equal to a n1 x1 plus a n2 x2 plus a n n xn plus f n of t. So you can see it's a little bit of a pain to write all those equations like this and try to solve it, okay, because it's way too many things to handle at a time. So I hope based on your experience from linear algebra, it makes sense to put it all together in a more compact form. Okay, so the matrix form for the same system would be, well, you write all the derivatives in a vector. Okay. That's going to be, I'm just going to avoid writing the dx1 dt, so let's call it as x1 prime. Okay. This is x2 prime, and this is xn prime. x1 prime, x2 prime, dot 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 xn prime. And without telling a lot of stories, I think all of you would agree that you could put all those coefficients into a matrix, a11, a12, a1n, an1, an2. So that is your n by n. It doesn't have to be even square, but we're going to focus on a square system. Okay, so I got n equations here. So it's a and n times the vector x1, x2, x3, n plus those outside set of functions which we call as the source or sink functions. Okay, f1 of t, f2 of t, fn of t. So it looks more compact when you put this into a matrix form. Okay, especially if you use a vector notation. So let's call this coefficient matrix as A, capital A. This is your vector of unknowns x here. This is some vector of functions f. And the left-hand side is a vector of all the derivatives. Let's call that as x prime. So this rather nasty looking system has a pretty easy looking appearance when you put it in a vector form. Okay. So the matrix notation for the above n by n system would be the following. The derivative of x as a vector, which is the vector with all the derivatives listed one after the other, equal to the coefficient matrix A times the vector of unknowns x plus some vector f. So when you say solve this, okay, I know it kind of, oh, just solve for x, is that it? But then that x contains all that all those functions there. Okay, so depending on how big your system is, it could be 3 functions or 4 functions. Okay. So the solution to this would be a vector of functions. Because when you solve differential equations, that's what you expect, right? You get functions out of that, some of which may look easy enough, some of which would be complicated. Okay. So this f here is the non-homogeneous term. As always, that is the term that is coming from outside. It's some kind of an external force if you think about your spring mass system. Okay. So if the f equal to 0, things are a little bit more easier. It's 0 with the vector, that means all of them are equal to 0. Okay. So you have x prime equal to x. So where A is a n by n matrix with numbers, x is a n by 1 vector with functions which are unknown at this point. We are trying to solve for it. Okay. This is the homogeneous system. So right now we have no idea how to solve this, so that would be a good place to start. Okay. We don't want to throw in a lot of things in there and complicate things. So let's start with the homogeneous system, understand that first, and if there is time, we'll look at a couple of easy non-homogeneous cases. So that is going to be the idea here. Okay. The rest of today's lecture and maybe part of tomorrow's lecture. But any questions about this notation? I know it's a little bit of a sudden change from differential equations to linear algebra at this point. Okay, your system of n differential equations, and somehow we are able to write it into this bizarre form, okay, which makes things look more compact, but doesn't change the end result there. Okay, we are trying to solve for all these functions. Okay, so this will be n functions here. All right, so first let's see how you would solve it without linear algebra, and hopefully that will be a motivation to do the rest. Okay. So let's take a 2x2 system. So solve two by two is bad enough, believe me. So if you go into 3x3, things get a little ugly, but 2x2 is dangerously close to being bad. So x1 prime equal to x2 and x2 prime equal to 2x1 plus x2. So right now you have no idea how to do this. Okay. So one technique which you could use without linear algebra is to do this by elimination. And just like if you had two variables x plus y equal to 3 and 2x plus 3y equal to 7. Okay. First technique you learn in your middle school is to eliminate one of these and then solve the other one. That's what Gaussian elimination does. Right? So the same idea here. Can we eliminate one of these? So this is a very easy system, okay, mind you that. So because the first one doesn't have a x1 term, okay, the second one looks pretty clean. So can we eliminate one of these and solve for the other? In this case, it's pretty easy, okay, easy within quotes, because right now you don't know what that easy means. So what I'll do is you see x1 prime equal to x2, and this is x2 prime, and since x2 is x1 prime, okay, I'm going to plug it into this equation here. So let me write that in detail. Observe closely this, it works in a very unique way, and if you're not catching that one step, it's difficult to understand what's going on. So since x2 is x1 prime, That is what the first equation is telling you. Okay. Look at the second equation. We can plug it into the second equation, which is x2 prime equal to 2x1 plus x2. That is the elimination process. So this x2 will go in here. So it's going to become x1 double prime, okay, because it's x2 prime equal to 2x1 plus x2 is x1 prime. Okay. So there you have it. You have eliminated your x2. But during that process, your equation became a second order equation. You had to give something. So this is x1 double prime minus x1 prime minus 2x1 equal to 0. You know how to solve this. Okay. We did this in the first or second week of classes. Write the characteristic equation for this. I know you've forgotten it, but let's just try to do a quick recap of that. It will be r square minus r minus 2 equal to 0. So just record that equation carefully. We'll come back to that equation later. So r square minus r minus 2 equal to 0. You know how to solve it. R minus 2 times r plus 1 equal to 0. So r1 equal to 2, r2 equal to negative 1. So you get x1 of t equal to c1 e to the power of r1t, which is c1 e to the power of 2t plus c2 e to the power of negative t. If you ask me, how did I get that one? I'll say, go back and look at chapter 2. Okay, that is case number 1. Okay, now you have x1, and you know that x1 prime is x2, so you get x2 as well. Since x2 equal to x1 prime, okay, take the derivative of this term by term. That will give you x2 of t. The derivative of the first term is going to be 2c1 e to the power of 2t and minus c2 e to the power of negative t. Okay, so, okay, not too bad. As I said, this is probably the easiest of the systems you could take, especially because the first one has only got one term on the right hand side. Okay, kind of made your life a little easy. Now let's, for academic reasons, let me just write it in the vector form. So x1 of t, x2 of t, x of t, because we got two variables or two functions here. So let us just list it in an organized way, x1, x2, and that's going to be c1 e to the 2t plus c2 e to the power of negative t. And the second one is 2c1 e to the power of 2t minus c2 e to the power of negative t. Now this is what I'm going to do. I'm going to kind of separate it out into two independent vectors. Okay, so this is going to be c1 times e to the power of 2t times the first vector, which is 1, 2. You might be thinking, why am I doing this? Well, I'll show you soon. Okay. So c1 e to the power of 2t times 1, 2 plus c2 times e to the power of negative t, sorry, times 1, negative 1. So it has got a format of some exponential function times a vector and an exponential function times a vector. That is what it looks like for a 2 by 2 system. Okay. So let's call this as the vector v1 and vector v2. Now, here's a small exercise for you. Okay, take that same system that I did just now, write it in the matrix form, find its eigenvalues and eigenvectors. So I don't want to erase that thing unless I'm completely done with this next part of the discussion. So that make sure that everything stays there. Okay. So this is what I had initially. So the vector form for this, all of you should know how to convert that into a matrix or vector form, would be x1 prime, x2 prime equal to, remember that this x2 is 0 x1 plus x2. Okay. So when you write the matrix, it's going to be 0 1 2 1. Times the vector x1 x2. Okay, so this is your coefficient matrix A. So my exercise for you, which you can do pretty quickly, is to find the eigenvalues and eigenvectors of this matrix A. It's a completely different problem now. Okay, that's what I think it is. So let me slowly start doing with this matrix. So the determinant of A minus lambda I would be, when you're doing this, just try to kind of keep comparing with what I just wrote above this. Okay. It's interesting to see how things evolve out of a completely different problem. So this is 0 minus lambda, which is negative lambda, 1, 2, 1 minus lambda. So that is negative lambda times 1 minus lambda minus 2 equal to 0. So that is lambda square minus lambda minus 2 equal to 0. Look at this equation now. Okay. You see how things kind of merge into each other. So you know the eigenvalues now. These are 2 and negative 1. Okay. And it's not some kind of weird coincidence that those were the values up there, e to the power of 2t and e to the power of negative t. Those were the eigenvalues for our matrix here. Okay. And if you find the eigenvectors for lambda equal to 2, the matrix A minus lambda I would be 0 1 2 1 minus 2 0 0 2, which is negative 2 1 2 negative 1. That looks pretty healthy because you get a row full of zeros, so you can reduce this to 1 negative 1 half 0 0. So an eigenvector would be, so x2 is free, okay, so x1 would be 1/2 u. So you can write 1/2 u. Okay. And it's just a practice that we try to avoid fractions when you do eigenvectors. Okay, you don't have to, but it looks better if you clean up that fraction. So you can pick u equal to 2, for example, and that gives you 1, 2. And there you have it. Okay. So the eigenvalue is sitting in the exponent, the eigenvector is multiplying right next to it. Now it will be a shock if the other one does not agree, right? So for lambda equal to -1, a minus -1 I is a plus I. So you just need to add the identity matrix to that 2 by 2. That's going to be just 1, 1, 2, 2, which is the same as 1, 1, 0, 0. Okay. And that gives you this as an eigenvector for the second eigenvalue as v2 equal to 1, -1, yeah, because x2 is free, okay, so x1 is negative x2, so 1, -1, which is sitting here. So you can see how these eigenvalues and eigenvectors are popping up in places which are unexpected now. Okay. So the eigenvalues came in the positions of the exponents there. Okay, so those this was your lambda 1. That is your v1. -1 was your lambda 2. And this is your v2. The only important thing is we should have an eigenvalue and eigenvector to fill in those terms. Okay, so I'll write a theorem pretty soon to make sure that this applies in a nice and easy way to all the problems we are going to do. All right, so I hope you understand why eigenvalues are important in this context. Okay, there are lots of other applications out there. We are just focusing on differential equations in the semester. Okay, so you can see how that helps you solve systems of equations without doing the elimination process. Okay. We'll do one more example, which is a slightly harder one to do it without linear algebra. Okay, and that will probably kind of help you understand why linear algebra is the way to go for this one. Okay, stick with 2 by 2 and still show that things could get worse. I think there is some construction going on in the building, and then you might hear some unpleasant noises. Okay, bear with that. Usually they have a lot more construction going on in the summer. This year we have been lucky that it's the last week of the semester. Usually they have a jackhammer on the roof. Okay, example 2. Example 2 has a very unique way of solving, okay, which I'll show you, but once again, our objective is to motivate you into sticking with eigenvalues. So x1 prime equal to 2x1 minus 3x2, and x2 prime equal to x1 minus 2x2. So once again, these equations are telling you how x1 changes with itself and also with the other component of the system. Okay, so if x1 and x2 are two animals in the same population, it's telling you how the population of that one particular species changes with itself and also with the presence of the other species. Maybe it's a predator-prey system. Okay, so if there is not enough food, this will decrease in time. If there is a lot of food, that will increase in time. So that is how the interaction happens in an ecosystem. So this 2 by 2 system is pretty easy to visualize in terms of what happens around. Maybe it's a competition between two companies. Okay, a lot of things that evolves with time. Okay, the problem here is that unlike the previous one, it's not easy to just do a straight elimination. Okay, but x1, x2 here, x1, x2 here, okay, not easy to eliminate like we did in the previous example. Because if you try to plug in x1 or x2 into the other one, okay, you cannot get rid of that second variable. It's still there. The previous case we were lucky because one of the equations had only one variable. So one of the mathematicians of the 19th century, D'Alembert, okay, or I think his name is D'Alembert or D'Alembert, I forgot. Okay. He devised a technique. He said that this could be done easily if you look at this as some kind of an algebraic process. Okay. So this is x1 prime, let's just call it as dx1 and x2 prime as dx2. Okay. We're just trying to solve it. Somehow we need to get rid of these variables or functions. So let's just give a new notation to it. So the d here stands for the derivative with respect to t. But when we're solving it, we're just going to forget about that fact that it's a derivative. Okay, it's some kind of an algebraic object. So we have dx1, capital dx1, equal to 2x1 minus 3x2, and capital dx2 equal to x1 minus 2x2. So what D'Alembert did was he kind of made the equations look like, okay, kind of cheating, looks like, these are just algebraic equations. Now what you can do is push everything to one side and write like this: d minus 2 x1 plus 3x2 equal to 0. And we have negative x1, because this goes to the left, plus d plus 2x2 equal to 0. Okay. Now we have all done this trick in middle school or high school. When you have equations like this, we want to eliminate one of them. Okay, just multiply the second equation by d minus 2 and add them together. So this is equation 1, that is equation 2. So multiply equation 2 by d minus 2. So the system looks like this now: d minus 2x1 plus 3x2 equal to 0. The second equation looks like this: minus of d minus 2x1 plus d minus 2 times d plus 2x2 equal to 0. You probably do, this is what you do in REF as well. Multiply a row with some number and add them, subtract them, right? You're doing the same technique here. But you have to be a little crafty to come up with these ideas, and that's what D'Alembert did. Okay. So if you add these two equations, these two cancel out. That's the elimination process here. So if you now add these two terms, this is d square minus 4, okay, d square minus 4 plus 3 times x2 equal to 0. And that's d square minus 1. X2 equal to 0. Okay. Now, we need to go back and think about what was d. That was a derivative with respect to t. Okay, so this is now x2 double prime minus x2 equal to 0. So we did the process of elimination, and then we retrieve what was initially supposed to be, right? D is capital D is d dt. So capital D square x2 is the second derivative of x2. Pretty clever. What's that? This term here, d square minus 4. Multiply those two. A minus b times a plus b. Still not convinced? You are adding the two, so this is d square minus 4. Then you have this plus 3. That's d square minus 4. These two got cancelled out. Oh, minus 4 plus 3. Yeah, the second one comes from the first one. Okay. All right. That was a pretty sophisticated way of eliminating, but we were successful. Okay. We can solve it. The characteristic equation for that one would be, so this is what you have, x2 double prime minus x2 equal to 0. Okay. That's going to be r square minus 1 equal to 0. So r equal to plus or minus 1. So x2 of t is c1 e to the power of t plus c2 e to the power of negative t. Okay. Again, all those things I'm just quickly referring back to chapter 2 about two real distinct roots for case number 1. Okay. All right, now we need to find x1. So I look back at my same system up there. Let me just write it here just for convenience. Okay, this is what you had. D minus 2 x1 plus 3x2 equal to 0. And negative x1 plus d plus 2x2 equal to 0. Okay. We found x2. Now we need to find x1. So I'll do something similar. So you can multiply the first equation by d plus 2. Okay. And you get d square minus 4 x1 plus 3 times d plus 2 x2 equal to 0. Okay. And I'll multiply the second equation by 3. Oh. So this one, because I'm trying to eliminate x2, okay. Multiply by 3. That way we'll get the same coefficient for the x2 term. So it's going to be negative 3 x1, or I can multiply by negative 3. So plus 3 times d plus 2 x2 equal to 0. My whole process was to get these two to cancel out. Okay. We need to eliminate x2, solve for x1. All right, we need to subtract these two because they're the same sign. Okay. So subtract. So you have d square minus 1 times x1 equal to 0. Now we should be a little careful here. Okay, so kind of looks like this. So your differential equation now is x1 double prime minus x1 equal to 0. So you have r square minus 1 equal to 0. When you solve this, you shouldn't put the same constant c1 and c2 because this came out of a different system at this point. Okay. So when you solve this, you have x1 of t. So this roots would be still r equal to plus or minus 1. Okay, same as what I did earlier. This will be some k1 e to the power of t plus k2 e to the power of negative t. You cannot call them as C1 and C2 because we solved it in a different way, and you cannot expect this constants here to be exactly the same as the previous one. Okay. So we have C1 and C2 here, K1 and K2 there. We need to kind of figure out what K1 and K2 are in terms of C1 and C2. So what I'll do is I'll make use of one of our differential equations to do this. Okay. So we have x1, which is k1 e to the t plus k2 e to the negative t. So x1 prime would be the derivative of that term, which is k1 e to the t minus k2 e to the power of negative t. That is my x1 prime. Equal to 2x1, which is 2 times k1 e to the power of t plus k2 e to the power of negative t. That is x1 prime equal to 2x1 minus 3x2, and x2 is up there. Minus 3 times c1 e to the t plus c2 e to the power of negative t. Oh gosh. Okay, now move terms across and get it into a form where you could compare the coefficients of the like terms. Okay, so this is going to be k1 e to the t, and you have 2 k1 e to the t. So bring it over here. That becomes negative k1 e to the power of t. Make sure that I'm not making any algebraic mistakes. Okay, it's a positive 2 k1. Yeah. Then you have minus k2 minus 2 k2 becomes minus 3 k2 e to the power of negative t. Equal to this part, which is negative 3 c1 e to the power of t minus 3 c2 e to the power of negative t. That helps you kind of make things compatible, okay, because otherwise these are two different functions. If you compare the coefficients of the like terms, you get k1 equal to 3c1 and 3k2 is 3c2, so k2 is c2. Hope I didn't make any mistakes, so let me just double check. K1. Yep. You can see it's a lot of work, even for a 2x2 system without a lot of fancy things going on. Okay, you don't want to do all that stuff. So now if you write in the vector form, you have x1 of t, x2 of t. X1 is what we just got here. So k1 is 3c1 e to the t plus c2 e to the negative t. Okay. And x2 of t is c1 e to the t plus c2 e to the negative t. Once again, and just for illustration purposes, I'm going to separate it out. Okay, so it's c1 e to the power of t times 3, 1 plus c2 e to the power of negative t times 1, 1. So that is my solution after some struggle. Okay. Now, once again, let's take the coefficient matrix of this, write it here. Can you find its eigenvalues and eigenvectors? So 2x2 system, you should be able to do it quickly. Okay. going to be -4 plus lambda square. Okay. Minus -3. Lambda square is, or lambda square minus 1 equal to 0. Okay, which is what I had it somewhere as the characteristic equation for both x1 and x2. Right? R square minus 1 equal to 0. So lambda equal to 1 and -1. And you can see the exponents there are actually 1 and -1. For lambda 1 equal to 1, a minus I is 1 -3, 1 -3. Which becomes 1 -3 0 0. X1 is basic, x2 is free, so you get x1 equal to 3u, and eigenvector is 3 1 if you pick u equal to 1 as your free variable. Look at how much work we had to do earlier to get the 3 1 and how much work you had to do here to get a 3 1. And for lambda 2 equal to -1, a plus I would be 2 -2 1 -1. Right? No. Added it to the wrong things. I should write it down actually. 2 -3 1 -2 plus 1 0 0 1. I shouldn't get too excited. 3 -3 1 -1. Once again, x1 is basic, x2 is free, so an eigenvector would be v2 equal to 1 1, okay, which is what we have here. So for corresponding eigenvalue of -1, that is a vector. Eigenvalue of +1, that's a vector. Okay. So if you have the eigenvalues and eigenvectors, solving a system of differential equations of any size would be pretty straightforward by just putting them in those appropriate positions. Okay. That is what we are going to do next, and that's going to be the main part of what we are trying to do here. So all this elimination process is just a waste of time because it takes a lot of time to do this by hand. All right, any questions about this before I kind of go for the punchline now? All right, so section 7.3, which is the last section of our semester. The eigenvalue method for system of differential equations. We are going to start with homogeneous system. We will talk about non-homogeneous things later if we get time, but don't worry about that right now. So system of homogeneous differential equations. Because the non-homogeneous part doesn't have to do anything with the eigenvalues. So, okay. All right, so let x prime equal to ax be, now you know what that means. Okay, that is a vector of all the functions, the derivative of that with respect to time. That is the matrix of all the coefficients, and that is the vector of all the unknowns. So let x prime equal to ax be a homogeneous system where x equal to x1, x2, xn. Okay, so there are n functions of time, and t is the independent variable. which means that time does not change with x1, x2, x3, and so on. All right, so this is what I want you to observe based on the examples we did earlier. Okay, we know the solution will look like that's what I tried to convince you with those two examples. Okay, we know the solution will look like e to the power of the eigenvalue times t times some vector v, which kind of reminds you of chapter 2, okay, where we saw that when we wrote a differential equation like this, ay double prime plus by prime plus cy equal to 0. The first thing that I mentioned, remember, was that y must look like this, e to the power of rx, so that those terms will add up properly. So same concept here. It's some multiple of an exponential function, okay, except that we are trying to somehow squeeze this eigenvalue concept into this. That's why we use lambda here instead of r, okay, but the same idea. So if you take, so this is going to be your x. Okay. So the solution of this would be of the form x equal to e to the power of lambda t times v. So x prime, to do a chain rule, lambda is a constant. Okay, so it's going to be lambda times e to the power of lambda t times v. Now let's plug this back into our differential equation here. Okay. So that becomes lambda times e to the power of lambda t times v equal to a times x would be e to the power of lambda t times v. Now if you bring all these terms to one side, you get a minus lambda times e to the power of lambda t times v equal to 0. I mentioned this once, you cannot combine apples and oranges. A is a n by n matrix. Okay. Lambda is a scalar. So if you want to make this operation possible, you need to squeeze in the n by n identity matrix there. Okay. So that's a minus lambda I times e to the power of lambda t times v equal to 0. Just so that you are having an n by n matrix here and here. And all of us hopefully will agree on one fact, that e to the power of lambda t cannot be equal to 0. Okay. That is a universal truth. It's an exponential function. Okay. No matter what part of the universe you go, that function you cannot get that equal to 0. So that is out of the picture. That leaves us with this equation, a minus lambda I times v equal to 0. Well, one possible case is if v equal to 0. Okay. Well, all of us know how beautiful that is. There's nothing, right? V equal to 0. Okay, so what? So that is useless. The other case is if it has infinitely many solutions. And you know where I'm going with this. That means the determinant of this matrix has to be equal to 0. Which means lambda has to be the eigenvalue for A. And V must be the corresponding eigenvector for that eigenvalue. So that is the theoretical reason why eigenvalues and eigenvectors are appearing in those places there. Okay, because the system must have a non-zero solution. If it is zero solution, then that's of no use. The only way the non-zero solution can happen is if you have those eigenvalues make it possible to have vectors which give you 0 on the right hand side. Okay, so now let's write our all important theorem. I have this theorem with you, okay, and if we, especially when the eigenvalues are real, life is super easy. When it's imaginary, you have to do a little bit of work, okay, but still life is easy. So let A be an n by n matrix. Every n by n matrix comes with n eigenvalues. Okay, that is the guarantee that linear algebra gives you. Doesn't matter what that looks like, okay, with eigenvalues. Lambda 1, lambda 2, lambda 3, up to lambda n, with corresponding eigenvectors. So each of these eigenvalues has its own eigenvector. That's what I'm trying to kind of state here. Okay, if that condition does not satisfy, we have a problem, but we don't have to worry about that. So with corresponding eigenvectors, V1, V2, V3, Bn. In other words, the algebraic and geometric multiplicities of each of these are the same. Okay, there is absolutely no inconsistency there. Okay, that's a very important thing, and then we will make sure that happens all the time. Then the general solution for the homogeneous system x prime equal to x is given by, drum roll, x of t equal to c1 e to the power of lambda 1 t times v1 plus c2 e to the power of lambda 2 t times v2. Okay. So any linear combination of these vectors will also be a solution, plus c3 e to the power of lambda 3 t times v3 plus cn e to the power of lambda n t times vn. Once again, this theorem will not hold in this form if you don't have enough eigenvectors to do this problem. Okay. That is not a situation that we are going to encounter in this course. We don't have time for it. Okay. So this theorem is only true if the algebraic and geometric multiplicities are the same for each eigenvalue. It doesn't have to be equal to 1. Okay. It could be repeated, but if it comes with the same number of eigenvectors, we are good. So if Mg is less than Ma, that is what you call as a defective matrix, which means that you no longer can do this theorem. Okay. Matrix is defective. And the theorem fails. So we don't have to worry about this part this semester. Okay. So at this point, if you know how to find the eigenvalues and eigenvectors, you can do this problem easily. Here's an example. So I'm going to kind of borrow an example from yesterday's lecture, okay, just so that I don't have to do a full 3 by 3 in its all full glory. Okay. So eigenvalues So let's do this. Example. Write the solution for the following linear system. The general solution, okay, for x1 prime equal to 8x1 plus 7x2 plus 7x3, x2 prime equal to negative 7x1 minus 6x2 minus 7x3, and x3 prime equal to 7x1 plus 7x2 plus 8x3. Believe me, you don't want to try elimination here. Okay, that's a terrible idea because you got three functions and you're just going to get lost in there. Well, the matrix equivalent of this would be x prime equal to this matrix, which should look familiar, or at least it should be in your notes somewhere. Okay. 7, 7, 8 times x. All right, so yesterday we found the eigenvalues to be I forgot which ones I wrote first or lambda, but that doesn't matter. Okay, lambda 1 equal to 8, lambda 2 equal to 1, lambda 3 equal to 1. And the corresponding eigenvectors were v1 equal to 1, negative 1, 1, v2 equal to negative 1, 1, 0, plus, and v3 equal to negative 1, 0, 1. Okay. This is what I call as a non-defective matrix, because even if those were with algebraic multiplicity of 2, okay, for this case, we were still able to get enough eigenvectors to complete this theorem. Okay. So it's not defective. And this one belongs to this, okay, because lambda 1, v1, that's a unique pair. I don't care which one is which out of these two. Okay. So you can just give those to corresponding eigenvalues there. No, that looks easy now because yesterday we did all the hard work behind the scenes. So we're kind of borrowing those things from that lecture. So don't just assume that this is a given. Okay. So the general solution would be x of t. Okay, that's what you're trying to solve. Once again, when you write it, okay, that is the vector with the 3 rows as x1, x2, and x3. Sometimes, students, they write this, they don't know what it means. So you write x of t in this case, the first row is x1, second row is x2, third row is x3, and that's equal to c1 e to the power of lambda 1t, which is 8t. Don't forget this t, okay, because otherwise it will be a number, e to the power of 8. So it's 8t times its eigenvector, which is 1, negative 1, 1, plus c2 e to the power of 1t, t, times its eigenvector, which is 1, negative 1, 1, 0. Okay. Don't forget that any multiple of these eigenvectors are also admissible here, okay, because u was a free variable, plus c3 e to the power of negative e to the power of t times negative 1, 0, 1. So no need to worry about any crazy elimination process or anything. Okay. Once again, I know the solution looks very cryptic when you write it in this form. Defective means the multiplicities are not. So if mg is less than ma, the matrix is defective. We're not going to solve those cases in this course, so you don't have to worry about it, but that is what it means by defective. Because the matrix is not going to work well in this particular theorem. Now, it's always good to understand what these rows mean. So x1 is the first row of this thing. Okay. X1 of t. You don't have to write this, but sometimes students, they kind of miss the plot when they look at this. Okay. C1, this first row here, C1 e to the power of 8t plus C2 e to the power of 8t times -1 and minus C3. So the first row here, it's corresponding to x1. So x2 of t is negative C1 e to the power of 8t plus C2 e to the power of t plus 0 e to the power of t. Okay. There's nothing there because that is 0. And x3 of t is C1 e to the power of 8t, that's the third row, plus 0 C2, that is 0, plus 1 C3. So this is row 1, this is row 2, and this is row 3. Where, which one? This one? Oh, yes, thank you. I didn't mean to recycle that one. Yep. So it's a very simple theorem to use if you know the eigenvalues and eigenvectors. Okay, all you have to do is plug it in. And if you don't have enough eigenvectors, you cannot do the theorem. You cannot force it to happen. Okay, unfortunately, it requires a lot more theoretical knowledge to do the case where mg is less than ma. So don't try those things now. Okay. How do we find those constants C1 and C2 and C3 and so on? Any idea? Been speaking for a while now. What do you think about now? What kind of information do we need to find C1, C2, C3? What kind of information did we use earlier when we solved for C1 and C2? Initial, yeah. So in this case, we need some kind of an initial vector x of 0 to solve for C1, C2, and C3. So as a sub question, okay, find the particular solution in the same example. If x of 0 as a vector is 0, 1, 1. I hope that is not too crazy to do. I just made it up myself, so I hope it's a consistent system. Okay. Remember that you are plugging in t equal to 0 here. Okay. So as much as it looks like a bad idea, e to the power of 0 is 1, so it's not as bad as it looks. Okay. So x1 of 0 is C1 minus C2 minus C3, and that's equal to 0. Okay. X2 of 0, and that's one of the reasons why I just wrote it out like that, so that when I solve for these constants, it's a little bit more easier for me to handle these. Okay. X2 of 0 is negative C1 plus C2, and that I gave you is equal to 1. And x3 of 0 is C1 plus C3. And that's also equal to 1 based on what I gave you. So all I can hope and pray for is that this is a consistent system, solve it. Okay. You don't have to use any fancy techniques. You could just solve it one by one. So right, C3 as 1 minus C1. If you want, you can do REF and all that, okay, to just show off your knowledge. So C2 is 1 plus C1. And you can just plug it into the first one. That's going to be C1 minus 1 plus C1 minus 1 minus C1 equal to 0. As long as I don't get 0 equal to 1 or something, I'm good. What do we get? I know one of these C1s will cancel out. What is C1 then? 2? Negative 2? Or negative 2? Let's start the argument now. Is it 0? Maybe I should just do it instead of asking. So is it negative 2 or 2? 2, okay. I think the same person is telling me two answers. So, all right. So C2 is, I don't want to spend another 15 minutes trying to figure out these numbers. And C3 is negative 1. Okay. So that will give you a particular solution for that initial set of values. In this case, it was kind of easy because some of those terms were mostly were with coefficients of 1. Okay, but in a more general case, you might want to just write a 3 by 3 and do an REF and do it in a more organized way. Okay, so it's a little bit too easy for a real system. Okay, then there's nothing fancy here. If you know how to find eigenvalues and eigenvectors, that's pretty much the end of the story. Any questions about this before I show you the bad one? So there is only one thing that you need to be careful here. Okay? That is, if you are dealing with imaginary eigenvalues, it's a slightly different story. So I'll do one example today and then probably one or two more examples tomorrow, depending on how you feel about it. Okay. The 2 by 2 imaginary eigenvalue case. It could be a bigger matrix, but we don't have time to deal with more complicated systems in this course, so that's why I'm just sticking with 2 by 2 imaginary case. Yesterday we mentioned something about this. If you have a 2 by 2 matrix with eigenvalues of A plus IB, then the second one has to be A minus IB. And if you know the eigenvector for this, V1 equal to U plus IB, then the eigenvector for this would be U minus IB, where I is the square root of -1 and I square is -1. And I'm assuming that none of you have taken a formal course in complex variables or anything. Okay, but when you write a term like this A is called the real part of lambda2, B is called the imaginary part of lambda2. It's just some kind of nomenclature for the world of complex numbers. Okay. So for this case, A is called the, it's written as RE for real, the real part of lambda2, which is and the B part is the imaginary part because it multiplies I, okay, or B or negative B, whichever you want to call it. Imaginary part of lambda2. Okay, so there's nothing sophisticated about it. You're just giving some names to it just for classification purposes. Okay. Once again, we're going to take advantage of this conjugate nature when we deal with solving a system of differential equations. Okay. So here is the theorem to help you deal with these kinds of problems. Okay. And I will also deal with or refer to this theorem as my lovely theorem because it makes my life easy. Theorem very important, very lovely. So let A be a 2 by 2 matrix. Now write this carefully. It will save you a lot of unnecessary work and stress when you do these problems. Okay. Some students, irrespective of how many other times I repeat this, they don't listen to me. They go through some other path, and it's a different story. So let A be a 2 by 2 matrix with eigenvalues. This is strictly for imaginary cases. Okay. Lambda 1, lambda 2 equal to A plus or minus IB. Now I don't care which one you call what. Okay. Yep. Plus IB be lambda 1 or A minus IB be lambda 1, that's your choice, with corresponding eigenvectors. V1, V2 equal to U plus or minus IV. Then so we have a pair there, eigenvalues, eigenvectors. Okay, each eigenvalue has a corresponding eigenvector. Then the general solution to the system x prime equal to ax. Remember that we are doing real valued problems here. Okay, you're taking a spring mass system or maybe a system with electrical circuit. You cannot tell people that, oh, this is imaginary system here, right? So your answer must look real. Okay, even if you have this I going on in the system, at the end of it, you should present the real solution to somebody who is asking for the answer. So the general solution to this is real valued, which means there is no I, because we are living in a real world. Okay, it's real valued and is a linear combination of the real and the imaginary parts of that's why I wrote those earlier. Real part is the one without I, imaginary part is the one with I, but you're not writing I there. This is just negative V. Okay. And the real and the imaginary parts of e to the power of lambda 1 t times V1. Now, what is special about this? Nothing special. If you want to write e to the power of lambda 2t times V2, that's your choice. Okay, just stick to one of them because of the conjugate property. If you just do one of these, you'll get the entire thing. Okay, and that's why I keep mentioning some students that take both and get into this whole mess of terms. Okay, so you could do or e to the power of lambda 2t times V2, but please, for goodness sakes, not both. Good thing is we'll get the answer after a couple of hours of a lot of math, which serves no purpose to your life. So what you do is find your eigenvalues and eigenvectors lambda 1, lambda 2, v1, v2. Okay, assuming that these are imaginary. If you find this one here, the other one is automatic because it's conjugate. Okay, so all we need is that one pair. Step 2, take this term e to the power of lambda 1 t times v1. Okay, use our famous Euler's identity. This is the life changer here. That is the one that helps you transform from the imaginary world to the real world and use this in engineering problems. Okay. Use Euler's identity e to the power of I theta equal to cosine theta plus I sin theta. Without it, you cannot extract the real and imaginary parts. Okay. This part here will tell you that is the real part, this is the imaginary part. So use Euler's identity, simplify this. So that takes some time, not a lot. Okay. So you have to do some algebra there. and then separate the real and imaginary parts. We have two functions here, the real function and imaginary function, okay, which are both independent of I, because the I is left behind when you write the imaginary part. It's just that number multiplying I. Okay. So it's a linear combination of those two terms, which means C1 times the first function plus C2 times the second function. That will give you the solution to this system, and it's real valued, which means there is no I in the answer. That's why engineering systems have real solutions, not imaginary solutions. Okay. Even if the math involves I, the solution is still real. All right, so I'll do an example with this tomorrow. I don't want to do one at this point and hurry through it. Okay, so up to here, including this, is what I expect for test number 6. So first time I'm doing test number 6 in any course, but so I'll do an example tomorrow. It's a pretty standard calculation. Okay, I mean, you know how to find eigenvalues, eigenvectors. Just do this step here. So we'll do that tomorrow, and then do a quick review for test number 6, and that will be it for the semester. All right, so that's it for today. Okay, I don't want to start an example and then kind of have a race with the clock here.
Thank you.
All right, so I'll see you. Yep.
Thank you. Thank you.
Thank you.